Hello students, we discussed six numericals in our previous video of moving charges and magnetism. We are discussing exercise numericals. Now let us do from the seventh numerical. So let me read it again. It's again a simple and straightforward numerical. So parallel current carrying wires. So two parallel current carrying wires A and B carrying current 8 ampere and 5 ampere. So 8 ampere is the current passing in one wire and 5 ampere in another wire, parallel. Both are basically parallel currents. So we know the formula for force. Yeah, I drew the diagram neatly. So 8 ampere, 5 ampere, and the separation between the wires 4 centimeter. So we know the formula. I've just written the formula: mu naught I1 I2 L by 2 pi r. So I'm just going to be a substitution after this. See, I just substituted. So mu naught value 4 pi into 10 power minus 7. I1 is 8 ampere, I2 is 5 ampere, and the length, estimate the force on a 10 centimeter section of wire. So that is basically L. So 10 into 10 power minus 2, 10 centimeter. So 10 into 10 power minus 2 meter by 2 pi r. So 2 pi again r, the separation between the wires. So don't confuse between r and L, that is important. Yeah, I just substituted. So most of the things will get cancelled. See, it's a simple, most of the terms. Yeah, you can see 2 pi got cancelled, 4 got cancelled with 8, and 10 power minus 2 already can cancel. So if I just write the remaining 2 to the 4, so 4 into 5 20 into 10 200, so 200 into 10 power minus 7 Newton, or 2 into 10 power minus 5 Newton. So this is the force experienced. See students, here I want to give one more important information. Suppose they have not asked the directions. Suppose if at all they ask the direction, if they are in same, if currents are in same direction, parallel currents, they experience an attractive force. So the wires, the current carrying wires basically experiences an attractive force, which you can identify using Fleming's left hand rule. Similarly, if the currents are anti-parallel, then the direction of force, they repel each other. So this information you should know. So here in this problem they have not asked. If at all they ask, means you can add the word attractive, because they are parallel current, so they attract each other. Yes, moving on to eighth problem. It is based on solenoid. So length of the solenoid is given. So 80. So length of the solenoid is given, which is 80 centimeter, and windings given. So it's 400 into 5 layers. So you can basically multiply 5 into 400, which is 2000. So 2000 turns. So you can take like that. And current is given 8 ampere, and we know the formula. B, magnetic field B is equal to mu naught Ni. Here it is case sensitive, small n. Small n stands for number of turns per unit length. Very important. So small n is equal to capital N by L, where capital N is the total number of turns and L is the length. So I'm going to use this capital N I by L only, because the total number of turns given. So this 2000 is basically capital N. Yeah, just I substituted the values you can see here. So mu naught 4 pi into 10 power minus 7. So total number of turns 2000 is the total number of turns. 2000 into current is 8 ampere into 8 by length is given 80 centimeter. So again I want to convert into meter. 80 into 10 power minus 2 meter. So if you simplify, you will get the answer. See, wherever possible I have just cancelled. 8 got cancelled, 1 0 I can cancel, power got cancelled, become minus 5. So 800 pi remaining is 800 pi into 10 power minus 5. I can write 8 pi into 10 power minus 3. You can stop here, or you can want multiply by pi also, which will come 25.12 into 10 power minus 3 Tesla. So whichever you feel like. So the final answer for the magnetic field will be 25.12 into 10 power minus 3 Tesla. Yes, moving on to ninth problem. So here you have to find torque. Basically it's a square coil, side is given 10 centimeter, and number of turns also has some number of turns, and current that is passing is 12 ampere, and coil is suspended vertically and the normal making angle 30 degree. So again it's so you have to be very careful. Normal making angle 30 degree means you can directly substitute yes no. So we need the angle what magnetic field makes with the normal. Always students they get confused, they will see the angle what the plane makes. So you have to you have to notice this point carefully. Always whenever any plane means, so you have to see the area vector. Area vector is nothing but the normal drawn to the plane. So whenever you see angle, you have to see angle between that area vector, that is normal. So here this problem it's a direct, they themselves have given normal, but other problems students have to be very careful here. So field strength is also given 0.8 Tesla. So you want to find torque. So you know the formula for torque, NIAB sine theta. Just we have to substitute and we will get the answer. So here I drew the square loop. So you can see here with whatever best tools available, I just tried my level best. Yeah, it's a square loop of 10 centimeter, and see the normal, I drew the normal. This is the normal, and that is making angle 30 degree with the magnetic field. So this is the horizontal magnetic field. I have written the formula also. Torque is equal to NIAB sine theta, and just substitute. So N value is given 20 turns and current value is given 12 ampere. So area of a square, you know, so it is 10 centimeter. So a square, so 10 into 10, then you have to convert 10 power minus 2 centimeter also. So let me together put 10 power minus 4, because 10 power minus 2 into 10 power minus 2, so 10 power minus 4, this is area. So into B, magnetic field value is given 0.8 Tesla, then sine 30. That's it. If you just simplify, you will get the answer. Very easy numerical. See, I made the substitutions, and wherever I cancel, I cancelled. So 2 also get cancelled. So 0.96 Newton meter is the torque experienced by the square coil. Yes, moving on to 10th problem. So here they have given two specifications. Two different magnetic fields and two different area and two different number of turns and two different resistance. They are asking you to compare the current sensitivity and voltage sensitivity of moving coil galvanometer. So which we have to do. Substituted the first moving coil galvanometer values. Number of turns are 30, and area is 3.6 into 10 power minus 3, and magnetic field is 0.25. K is constant, identical for both the moving coil galvanometers. So it will get cancelled, so we need not worry. So I have just taken it as K. So similarly, I have substituted the values for the second moving coil galvanometer. 42 is the number of turn, 1.8 into 10 power minus 3, and then 0.5 is the magnetic field by K. So now we have to do M2 by M1, because they have asked the ratio of M2 by M1. See, I have made the cancellation. Mostly all terms will get cancelled. So only a simple table only. So 7 by 5, you can stop here, or if you want, you can write it as 1.4. So the ratio basically is 7 is to 5. So whichever way you can express your answer, you will be given marks. So this is the ratio between the second MCG and the first MCG. So M2 by M1 and current sensitivity. So similarly, we have to find voltage sensitivity also. So we know that is subdivision B. So phi by V basically. So you know the formula NAB by K, and you just have to include the resistance, where G is the galvanometer resistance, and that is also given in your book. It is given R. So you can take it as R also. See, I wrote the values for voltage sensitivity. Again, the same values are numerator, there is no change. it is the same value denominator. Along with K, you just have to multiply the resistance value 10. For M1 I have written, similarly for M2 also I have written. Now I have to go for M2 by M1. See, M2 by M1, the numerator value is already, I found it 7 by 5, so which I am directly putting it. So it is there in the denominator, so I wrote the reciprocal, so 10 by 14. So this will give me the ratio of voltage sensitivity, and if you just see here also, everything gets cancelled. So here the voltage sensitivity, ratio of voltage sensitivity is coming 1 is to 1. So 7 by 5 is the ratio of current sensitivity, and 1 is to 1 is the ratio of voltage sensitivity. Yeah, now we'll move on to the 11th problem. It's again a very easy problem, again a input direct substitution kind of problem only. Magnetic field is given, field strength is 6.5 into 10 power minus 4 Tesla. They have given it in Gauss, and they have given the equivalent scale also. And the speed of the electron is given, so 4.8 into 10 power 6 meter per second. And see, here is the key word in this question. So normal to the field, so this is the key word in the question. So charged particle kept perpendicular to the magnetic field. So students, are able to guess what will happen? A charged particle moving in a perpendicular magnetic field. What will happen? Yes, of course, Lorentz force, magnetic Lorentz force. But what will happen to the charged particle? Yes, it will move in circular path. Charged particle will move in the circular path. So we can equate magnetic Lorentz force, so BQV sine theta sine 90. So BQV, we will equate anything which revolves, possesses centripetal force, so mv square by r. So this is the equation. So yes, so shuffling, so we want radius, so r is equal to mv by bq. 1v gets cancelled, so we know the formula. This formula directly you can substitute into. Just for explaining, I wrote the previous formula also. Just a substitution after this. Mass of electron, basically if you know beforehand it will be good. Mass of electron, mass of proton, charge of electron and all, if you know by heartedly, it will be easy for you. Anyhow, it is given here, so just I have substituted. See, if you look at the powers, I have just written in this way. So everything gets cancelled, almost. Minus 10 plus 6 plus 4 10 29, so minus 31 plus 29, so minus 2. So power we can deal separately, and you just have to deal the numbers separately. So if you solve, you will get the final answer 4.2. so if you solve this, you will get 4.2 into 10 power minus 2 meter. So this is the radius of the electron, which is moving in a circular orbit. So moving on to the last problem. So just a continuation of the previous problem only. So it's not anything new, input is not given. Only you have to just find the frequency of the revolving electron. So you know the formula for the frequency of the charged particle which is revolving. So general formula is bq by 2 pi m. You can work out that previous step from there. V is equal to r omega, omega is equal to 2 pi f. So you can do the substitution and get the formula, or if you know that directly, you can substitute the formula also. bq by 2 pi m. Here electron, so I just wrote be by 2 pi m, then just substitution only. So same manner, see, power I have written separately, so minus 4 minus 19, the minus 31 comes to the numerator, so plus 31, so 10 power 8. So if you solve, you will get 0.1818 into 10 power 8. So you can write it as 18.18 into 10 power 6, and 10 power 6, you know, you can write it as megahertz. So the frequency of the revolving electron will be 18.18 megahertz. Oh, there is one more question also. Does the answer depend on the speed of the electron? So what's your guess? So look at the formula of frequency. So you don't find speed in this formula. So it only depends on the magnetic field strength, and then the charge, then the mass. So speed, so irrespective. So it does not depend on the speed of the electron. So thank you, children. So we have worked out all the 12 numericals of this lesson, moving charges and magnetism. Already we have uploaded a video on the lesson alternating current. So this moving charge also gets over. So I'll try to put the exercise numericals of other lessons also. Thank you, students. All the very best. So do well in this upcoming board exam. Thank you.